Okay, so let's begin. I'll just share my screen. Let me know if it's visible. Okay, one second. All right. So first of all, we saw last week gradients, right? So grad f is defined as a vector valued function, and it is basically a vector that contains the partial derivatives of some function f with respect to each of the variables that we have. So here we have, like, we can have, normally it's just x, then we have just real valued functions, and then we can have xy, and basically x1 to xn we can have any number of variables. Okay, so for that, the gradient, the grad f, is a vector that contains n elements, and each element is the partial derivative of the function with respect to that variable. Okay, so now the directional derivative of a function at some point. So this is like a point in this n dimensional space because we have n values in the coordinates. So here the directional derivative of the function f at this point in the direction of some specific vector v is given by the dot product of the gradients, so grad f, at this point. So we are evaluating this function by inputting these values with the unit vector in the direction of v. So basically we have v, we have to we have to normalize it basically, or make it into a vector of length 1, turn it into a unit vector. So we take v divided by the norm of v. Okay, and the directional derivative in the direction of this v is just this. Okay, so now the unit vector, like, we can find it from this only. So if we are finding like steepest ascent, or we're trying to maximize the function, then the unit vector, or the direction in which we're maximizing, that is given by the gradient divided by the norm of the gradient at that point, whatever point you have. And similarly, if you are minimizing the function, or you have steepest descent, then it's the same thing except you multiply by a minus sign in front. Okay. And suppose they're asking that, rate of change is, there is no rate of change. And so we are not looking for ascent or descent, then f of u is 0. That means u is orthogonal to grad f. So this, like, it's better to see some examples, so let's go to that first. Okay, so we have this function here. So this is from an activity only. I chose it because it covers a lot. Okay, so first of all, we're
Can you
given
please show
some
the
function.
previous notes,
What?
previous tabular column?
You're not clear, can you please repeat?
Can you please show the previous tabular column?
This one?
Yes, ma'am.
Oh, this is in the lecture. So this is in the first lecture only. I just took it from there only. But the unit vector, that is the direction in which you are finding the directional derivative of function at some point. That is basically if you are maximizing the function, or you have steepest ascent, is just the gradient at that point divided by the norm of this thing only. And if you have descent, then you have just that thing in front. You add a minus sign. So basically, it makes sense, right? You are minimizing it, so that's why you're multiplying it by a minus sign. And this basically means that at that point, f of u is equal to 0. That means there is no change. Rate of change is like a constant. So then u is like some vector that is just orthogonal to whatever grad f we get.
Excuse me, ma'am.
Yeah.
Ma'am, can you please tell how to find the gradient of a function? Like,
Okay. So gradient of a function, so let's see it here only. Okay.
yes,
So
ma'am.
that is this problem that we have here. So they've given us some function from R2 to R. So it's a scalar valued function because the output is a scalar. Okay. And it's from R2 because we have x and y. So this is given as this function e raised to x square plus xy plus y cube. Okay. So now they have asked a few things. What is the gradient? We need to compute the gradient here. You
Yes.
also need to find like f of xy increases most rapidly in the direction of something at point. So basically, if we have to check this, and so what we have is we need to compute the directional derivative. So let's just do that. So first step is to calculate the gradient. Okay, so let's do that. So for this particular function, we want to compute the gradient. Okay, this one. So gradient is basically a vector, right? It's a vector. The first f of x y is basically here it's just because we just have x and y, it's a vector that contains the first element is the partial derivative of f with respect to x, and the second element is the partial derivative of x with respect to y. That's it. And for any number of variables it's just going to be the partial derivative of f with respect to that random variable, that variable. Okay. So
Okay.
here, for this particular function, let's see. So they've given this. So let's calculate the partial derivative of f with respect to x. Okay. So for this, it's e raised to whatever. So the derivative, like when we're taking the partial derivative of a function with respect to some variable, we're treating the other variable as a constant, right? So, but because this is e raised to something, uh, the derivative of e raised to anything is e raised to that only. So partial of f with respect to x is equal to, first we'll keep the e raised to whatever part the same. So e raised to x squared plus xy plus y cube. Now we need to apply chain rule because like first we'll take the derivative of the outside function. Now this is also a function. So now we need to take the derivative of that with respect to x. So here the inside function, what is its derivative with respect to x? Just if we take the inside function as a separate function. So with respect to x, what is the partial derivative? Anyone?
2x plus y.
Yeah.
2x plus y.
Yeah, because y is being treated as a constant. We don't care about this y cube, and just we're just taking the derivative as we do as usual. So chain rule application, this is going to get multiplied by 2x plus y. Okay, so that is this one, the partial derivative of f with respect to x. And now let's calculate partial of f with respect to y. So this first part is going to stay the same, so I'll just copy it. Oops. Oh, okay, I'll just write it. Formatting issue. So because again we're taking the derivative with respect to y here, the partial derivative e, this whole part is going to stay put. That is just a property of e. So x square plus xy plus y cube. Now we have to multiply it by the partial derivative of the inside function with respect to y. So what is that here? What is the partial derivative of this with respect to y?
X plus 3y square.
Yeah. Correct, because x is being treated as a constant. So this is just going to be the constant times 3x. Correct. Okay, so now the gradient, I'll just write it here. So now the gradient is just a vector with these two values. Okay, so we can write that. So the first value is just e raised to x square plus x y plus y cube times 2x plus y, and the second element, it's a vector, so first element and the second element is just this part. Okay, so that is e raised to x square plus xy plus y cube. Okay, and we'll multiply it by this x plus 3y square. So this whole thing is the gradient vector. The first element is the partial derivative of the given function with respect to x. The second element is the partial derivative of the function with respect to y. That's it. So if we had z, then we take the partial derivative of the function with respect to z. That would be another element. So basically, if you are like the domain is like R2, then the vector, the gradient vector, is going to have two elements. So if this was from R3, then this would have three elements, and Rn basically n elements in the gradient vector. Okay, so remember that. Now here we can see that none of these given options satisfies this particular gradient, so these are all wrong. Okay, now we have to check like the direction in which the function increases most rapidly and at this point. So they've given some points, so we have to compute the directional derivative, okay, and we want to get the maximum of that. So here, first of all, we will evaluate the gradient at this given point, okay. So 1 1 they've given, that is equal to, so this is going to be a vector, okay. So we'll just put in 1 for x and 1 for y. That is all we have to do. So here e raised to, so 1 square plus 1 plus 1. So basically e raised to 3 is the first element times. Now 2 into 1 plus 1 is 3. And here the same thing, e cube is going to stay put. And then we have 1 plus 3 times 1 square, that is 4. Okay, so this is basically 3e cube 4e cube. So this is the value of the gradient at the given point. Now we want to find the direction. Okay, so the direction that maximizes the function. And for that, we just have to compute u as we saw here. Okay, so u, when we take gradient of f divided by the norm of this gradient at whatever point been given. So because we want maximum, we'll just calculate this. Okay, so let's calculate that. So u is equal to, so gradient of f at 1 1 divided by the norm of gradient f at 1. Okay, so here that is equal to this 3e cubed 4e cube. Okay, and we'll divide it by basically just the norm of this vector. So that means we'll have the square root. Okay, we'll square and add just general norm form. So we have 9 e raised to 6 plus 16 e raised to 6. So that is equal to, so this is going to be 25 e raised to 6. This whole thing, that is equal to 25 e raised to 6. The square root, that is 5 e raised to 3, right? So basically we can, that's just a constant, so we can pull that out. So we'll have 1 by 5 e raised to 3, this vector. And because we have e raised to 3 commons, we can also cancel this out. So each e raised to 3 gets cancelled. We can like pull it out of the vector. So this basically is just 1 by 5, 3, 4. So this is the direction. This u is basically a vector. So in the direction of this vector, the given function f increases most rapidly at the point. So any doubts
Ma'am, I
here?
just have a doubt. How do we
Ma'am,
find whether it increases or decreases?
ma'am,
So if it decreases, then we'll just multiply this by minus.
Ma'am, can you please show like how did you find this formula? Because like in lecture video sir explained and I could not understand. So can you please show that
What
how?
what what?
Ma'am, this
ma'am,
formula u
One
equals.
second, one second. Uh, yeah. So that you go first.
Yes, ma'am. Ma'am, I just wanted to know if you can please tell how this formula came about u equals to gradient of f. Because in lecture video, sir explained, but I could not understand completely. So, ma'am, can you please explain that how this formula how you have obtained for finding this direction?
ma'am,
Okay.
excuse me, ma'am.
Yeah.
Ma'am, 5, how, why did you written 5 e to the power 3? It is 5, 25 e to the power 6 under root.
E to, so it's square root of 25 e raised to 6. So when we take the square root, e raised to 6 is basically e raised to 3 squared. So when you take the square root, square root of 25 is 5. Square root of e raised to 6 is e raised to 3.
Okay,
Yeah.
okay,
Yeah. And then we cancel out the common e raised to 3 here.
okay, okay.
Yeah. So,
Ma'am, hello.
yeah.
Ma'am, here you divide it by norm of grade, right?
Yeah.
But ma'am, which I asked you in previously, there you said that we didn't divide it by norm because we don't want to find the unit vector.
Mm-hmm.
But when we need to divide it by norm and when not to, I don't understand that.
So in that question, basically, like just from the options, like that is what I get. I hear also, like the
Mm-hmm.
general form is like you always have to take the unit vector, but from what I've seen, like they can also specify it's not unit vector because in MLF, which is uh, data science diploma, like a course in that, you also have this stuff in that you have linear algebra and all that. So in that, they specifically said you don't have to take a unit vector, you just find it in the general direction. So it's not like set in stone that the direction has like we take the unit vector because it makes our computations easier. That is the thing, and it's generally done. But just because we like the direction is still the same, even if you don't divide it by the norm of the vector. So you just have to go through the options, like because in the course we have the unit vector, so you're generally going to be dividing it by the norm. But like in the practice assignment, uh, they like the options didn't have the unit vector, but the direction matched. So from that
Mm-hmm.
you just have to see what applies. But the main value of the vector has to stay put. Like 3, 4 here has to stay put.
Mm-hmm.
So if the
Okay.
value is positive, do we say it is increasing?
Yeah. So no. You take the value to be positive, then the function is increasing. If I wanted to find decrease, then I would just multiply this by minus sign.
Yes.
Yeah.
So, ma'am, for our easy computation, we just divide it by your unit
Yeah.
by
Yeah.
norm, right?
Yeah.
Okay. Okay.
Yeah. So basically they're equivalent because the direction is staying the same. Because see, if you have like say this, okay?
Mm-hmm.
Now you have this line. Alright? So suppose this is the vector v.
Mm-hmm.
Okay, so we want to find the directional derivative in this direction. Now, what we are taking the unit vector to be is just this v, but like with norm 1. So it's basically this is going to be u, and this is just v divided by norm of v. Okay, so as you can see, the direction is still the same. We just scaled it. We just do this to make our calculations easier. And this is generally done, but the direction is still the same. So it's not like a different vector.
Okay. Okay.
Yeah.
Okay, ma'am.
Okay.
Okay,
Now
ma'am.
let's go to the last point. So we want to find the direction in which we have steepest descent. Okay, like decreases most rapidly means steepest descent. So let's find that. So that means we'll find u is equal to minus. Now here the they've given the point 1 minus 1. So first we need to compute the gradient at this point, and then we'll find, because it's descent, we'll find minus grad f of 1 minus 1, same thing. Okay, it's just we'll have a minus in the front. So first we'll compute this. We'll move this here. Okay, so they have given us, okay, okay, so what did we compute this to be? All right, so this is basically the gradient function that is going to stay put. So now we'll just put in these values of x and y. So what do we get then? Let's see, e raised to 1 squared plus, okay, so here we just have e, because x square is 1 squared plus xy, so that's 1 minus 1, so 1 minus 1, that is going to 0, and y cubed is basically minus 1 cubed. So what we have is e raised to 1 sec. Yeah. Let me just check once. Okay. Oh yeah. Okay. So we have. Let's just bring this here again. So this is the gradient. Oh God. Okay, fine. So I can see it from here. I'll just zoom out a bit. It's visible, right?
Yes, ma'am.
Yeah. Okay. Okay. So for 1 minus 1, the first value is going to become, so we have e raised to x squared, that is just 1, plus xy minus 1 plus y cubed, so that is minus, okay, and then we'll have 2x plus y, so 2x is 2 minus 1, that is just 1, and then we have here e raised to the same thing, so e raised to minus 1, I'll just put it directly, and then 1 plus 3y squared, so y squared is just 1 still, so what we're left with is 4. So that is equal to minus 1, 4 e raised to minus 1. Okay, so this is what we have. So this is the gradient at this given point, right? That is the point now. Okay. So now we want to find u, and we want to find steepest descent. So it's going to be that only that we had earlier with minus sign. So u is equal to minus grad of f of 1 minus 1. We will divide it by norm of f of 1. Okay, so that is equal to minus e of minus 1 minus 4 e of minus 1. And what is going to be the denominator now?
Root 17 e to the power minus 2.
So how are we getting 17? So let's do the like full writing out now. So first we'll have root, and then the first value we'll square it. So that is just e minus 1 raised to 2. So e raised to minus 2 plus 16 e raised to minus 2, right? So this is equal
Yes,
to 1 by root 17,
yes, ma'am.
and e raised to minus 2, we'll take the square root of that. That's just e raised to minus 1.
Yeah, okay, ma'am. Yes, ma'am.
So e raised to minus 1. And also we can see the numerator has e raised to minus 1. So we can just cancel it out, right?
Yes, ma'am.
So directly we'll just forget this also, and we'll have minus 1 minus 4. So this is the u that gives us, yeah, so that matches this answer. So here both of our answers match the options given, so this is correct. Okay, so here we wanted to maximize, so we computed the gradient at the given point. Okay, and then to get the direction we also had to divide by the norm. So that is basically what gave us 1 by 534. So this is the first, like, the second last option is correct. And then similarly, in the last option they want us to get the steepest descent, right? So we did the same process, like the gradient evaluated at the given point. Here we had a different point, and then we had a minus sign in front because we want to minimize the function, decreases the function, decreases most rapidly or steepest descent. So same process again, just a minus in the front, and then that gave us 1 by root 17 minus 1 minus 4, and that is just this. Okay, any doubts here?
Ma'am, can you please move to the previous slide?
Which slide? This one.
Yes, ma'am. Ma'am, in this last no change one, now can you please explain it on graph that how this will appear on graph when fq is equal to 0, u is
So
also.
the thing is, like, the professor says in the beginning, we have so many variables here. It's like so many dimensions, we can't always graph it. But what this is saying is, or also because, we could have like n dimensional, or see R6, suppose it's an R6, then we can't have a graph for that. So orthogonal also is like, we say it's equal to perpendicular, but orthogonal is more general. Perpendicular specifically means 90 degrees between two vectors. So if two vectors are perpendicular, that means there's 90 degrees between them. Orthogonal is like, yeah, it's 90 degrees in two dimensions, but also the main thing is that their dot product has to be zero. So in perpendicular also, if two vectors are perpendicular, their dot product is zero. But we also specify that if the vectors themselves are zero, like, if you have, suppose, some vector and the zero vector, so that dot product is still zero. But we can't say that, some vector is perpendicular to the zero vector. But because orthogonal is more general, we can say, yeah, every vector is orthogonal to the zero vector. So basically what I'm trying to say is, don't depend on graphs here, because you're going to see many dimensions, right? Yeah, basically we're learning this maths, we can apply it to data, and data is going to have like so many values. So here what you just have to know is that the function, like in terms of the directional derivative, like there is no change to the function, the value of the function is going to stay put. So here basically when you have some u such that, at that point you have this, then what you are getting is function is increasing, and it's increasing like getting to its maximum value, and vice versa. For this, we're finding the function's minimum value. But here basically what is the function's value is staying the same. So the rate of change is basically zero because it's not changing at all. So that means that u is orthogonal to grad f. So you have like you have to, like, from the given options, you just have to take the dot product. You have to compute grad f like we did here. Okay. And then from the
Yes.
given options, you just have to see which given u has dot product 0 with the grad, and that is going to be the u that, the function is like not increasing or decreasing, rate of change is 0.
So, ma'am, between which two vectors we do the dot product, ma'am?
So this, like, here they haven't specified it, but basically this is grad f at some specific point. You
Yes.
want, yeah. So this grad f is one vector at that point, and then u is also a vector. So when you have dot product of u and grad f is equal to
Oh,
0,
okay.
then so u is going to be given to you in the options there, because you can have many possible u where the dot product is 0. Okay, so that is the logic here. So we have another problem. Okay, everyone is clear with this problem, right?
Yes, ma'am.
Okay, so now we have another problem, and this is basically saying we have a function from R3 to R. So that means that the gradient vector is going to have three elements, right? That just tells us this. And the function is given as alpha x plus beta xy square plus gamma yz square. That is the function. We don't know what these values are. Now, if the maximum value of the directional derivative of f of xyz at 111, so this is basically a point in R3, is in the direction parallel to x-axis and has magnitude 5, then, so basically we need to just find out what is the function. Now, based on what we've been given, we need to write down like what we know. Okay, so we know that maximum value of directional derivative at 111 is in the direction parallel to x-axis and has magnitude 5. So what does it mean that it's parallel to x-axis? Does anyone know?
The tangent that will be zero, ma'am. Like,
Parallel to x-axis, like, you mean it's in the direction of x-axis only, basically, because if x-axis, like, because this is R3, so let's see it like this. So we'll have, okay, so if we,
Ma'am, it means 100.
exactly. So 100 is on x-axis. So any, like, you can scale it anywhere. So that is the direction that is parallel to x-axis. X-axis itself is parallel to itself also. So in the direction parallel to x-axis means you just have to take the direction as 100, because this is basically any, um like, you can scale it by any amount. Okay, and then it's still going to be parallel to x-axis. That is basically what you have to know. Now, they've also said that the magnitude of this direction is 5. So now, because this is the direction, if the magnitude is 5, that means, what is the magnitude? Like, you have to take the square root and then the square of each element and the sum. So that means that basically, if we had just 5, one second, if we had just 5 times 100, then that is equal to just 500, and we can see that if we take its norm, it's just 25 plus 0 plus 0, like you square each element, that is just 5. So this basically means that this particular direction is parallel to x-axis and also has magnitude 5. Okay, so this is the direction, like, basically the maximum value of the directional derivative at this point is in this direction. Okay, that is what we know. And also we have that, oh, we also have this function given, so we need to calculate, to find the maximum value of the directional derivative, we at least need the derivative or the gradient, so we also need that. So just for this function, let's calculate the gradient vector also. One second. Okay. So now the gradient function f of x y z is equal to, now first element is going to be the partial derivative of this function with respect to x. So here alpha, beta and gamma are just some constants. So
Excuse me, ma'am.
yeah,
I'm sorry to disturb, but ma'am, this 5, ma'am, is this value of u?
no, this is the magnitude. It's the norm of this direction.
Norm, this is norm. Okay, ma'am.
Yeah, magnitude is basically norm. We don't use magnitude
Yes,
in
ma'am.
the
Norm.
stuff more physics, but
Yes,
norm
ma'am.
is linear algebra. So here
Okay.
they use magnitude. Okay. So now we're just taking the partial derivative. The first element of the gradient vector has to be the partial derivative of the function with respect to x. So what is the partial derivative of this with respect to x? Right here.
Alpha plus,
The partial derivative of just this with respect to x.
yeah, that is alpha plus beta y square.
Yeah, correct. So because alpha is some constant, and then here also x is going to go away. So we have alpha plus beta y square. Yeah. And then the next element is going to be the partial derivative of the function with respect to y. So what is that?
Beta
Y
x gamma z square.
no, 2
No.
beta x.
Yeah,
Okay, 2 beta.
exactly.
Yes, no, 2 beta.
2 beta because y is treating only y as the variable, right? So you have to take its derivative in the normal way only. And x,
So first we're differentiating with respect to x and then y and then z.
because that is what the gradient is. It is a vector where each element is the partial derivative of the function with respect to each whatever variable you have. So first we got it for x, then y, then z.
Yes, ma'am.
Yeah. And then we have, yeah. So y is going to stay put also. And then yeah, and the, oh, there's a y element in the last part also. So that is going to go away. So what we're left is, okay, I'll just move this here. One second. One second. Okay, formatted. So now we are continuing with the partial derivative of the function with respect to y. Okay, so it's, there's no YouTube link now because of some technical issues. It's being recorded. We are going to post it to the channel after the session is done. So you can find the link. You'll be able to find the link in your calendar. Okay, so
Gamma z square
yeah,
plan.
yeah, gamma z square, correct. So that is what we left with, gamma z square. And now we want the partial derivative of the function with respect to z. That is the third element of this vector, gradient vector. So what is that? So the first two don't have any z component, and then so we just have one part, and that is 2 gamma y z. So this is our gradient vector. Okay. So what the question is saying is that the maximum value of this directional derivative of this is this at this. So now we also like we saw here, to get to the directional derivative we first have to get the value of the function here. So let's do that also. So we'll put in, like for we'll put in xyz is equal to 111 into this, and then we'll have the directional derivative, and then what they're saying is it is in the direction this is this. So that means we'll equate it to what we got here. This is the direction we got, this part first, so we just equate. So first we'll put in xyz is equal to 111 in this gradient. Okay, so gradient f of 111, that is equal to, so we don't know alpha beta gamma, we're just going to keep them as it is. We're putting these values for xyz. So what is the first element then? This is y square.
Alpha plus beta.
Yeah, so we have alpha plus beta because y is equal to 1, we're putting that in. Now the second element is
Twice beta plus gamma.
we're put xy, we're putting in 1 for x, we're putting in 1 for y, but put also we have z square here, we're putting in 1 for z. So what we're left with here is going to be 2 beta times 1 into 1, so just 2 beta, and this is also 1 squared. So what we have here is 2 beta plus gamma, right?
Yes.
And then in the last one we just have 2
2
beta.
gamma.
Yeah. And they've said that this is in the direction of this is this. We found that is 500. So we'll just equate. Okay. So that means this is equal to 500 based on what they've given us only. So now all we have to do is equate coefficients. So alpha plus beta is equal to 5, and also 2 gamma is equal to 0, which means that gamma is equal to 0. And here we have 2 beta plus gamma is equal to 0. That means 2 beta, because gamma is equal to 0, so that means 2 beta is equal to 0, which implies
Alpha
that
is
beta
5.
is equal to 0. So that
Alpha
means
is
we
5.
just have alpha is equal to 5. Correct. Okay. So now all we have to do is take this alpha is equal to 5, beta is equal to 0, gamma
Okay,
is
so del f of 1 comma 1 comma 1, is it like the value of the magnitude?
sorry, I didn't get that. Can you please repeat?
So why are we putting the del f of 1 comma 1 comma 1 to 5 comma 0 comma 0?
We have to, there, like in the question it's given that, one sec, sorry, stream software. All right, is my screen visible?
Yes, ma'am.
Yes, ma'am.
Okay, this is better. Okay, so they've said that the in the question only it's given that the maximum value of the directional derivative of f of x y z at this. So this is the directional derivative at this 111. Okay,
Yes, ma'am.
so that is in the direction parallel to x-axis. Parallel to x-axis means any like 100, so any form of that. Okay, and they've also said that it has magnitude 5. So if it has to have magnitude 5, then that means the first element has to be 5, because doing all of this gives magnitude 5, which means it's norm. Magnitude is norm. So based on that only, we got this. So whatever we get as the directional derivative, that has to be equal to this. Okay. And so to get to the directional derivative, first we got the gradient vector, right? That is just a vector with 3 elements because we're in R3, and each element is a partial derivative of the function with respect to whatever variable we have. So this is the partial derivative with respect to x, and then y, and then z. Okay, so because it's at 111, this specific point, we have to evaluate the gradient at that point. So we got that. Okay, we just put in 111 for x, y, and z and evaluated this, and they've just said it's in this direction. That means we just set it equal to this direction that we found.
Sorry, ma'am, but how many more questions do we have?
We don't have that many questions today. You'll see a couple more only, and then it's general doubts because there is another session for week 10, and there's not much in week 10 basically. So that's why only a couple more questions only. Okay, is it visible now?
Yes, ma'am, it's visible.
Yeah. All right. So based on these values that we found, we just have to put it in this. Okay. So what we have then finally is f of x, y, z, that is equal to, now we found out that beta and gamma are zero, so these all are going to zero. Now alpha is the only one that matters. We found alpha is 5, so what we're left with is 5x. And this is the only function that satisfies all of this. So from here, the only answer is this. Okay? Clear? I took
Yes, ma'am.
Yeah, I took this question because this part is a little tricky. But generally, like you're going to be given like direction parallel to some z axis, suppose, then this would be 0, 0, 1. So similarly, if it was direction parallel to y axis, what would we have here?
010.
Exactly. And then magnitude, because it's just one, then we can just multiply it by whatever magnitude it has to have. So here it's this. Okay.
Okay, ma'am.
Yeah, and then the general form is going to stay the same. You always have to get the gradient function, and then you have to evaluate it at the given point also. And then you here we just have to equate. Okay, so let's go to a tangent, like tangent line type problem. So I have this here. So this is just from the solve with us. I'll just zoom in. Okay, yeah. So if you have some function f(x, y) on a domain R2, and then this is this. So parametric function is basically you have x, and then the parameter here is p, so that is equal to a plus tu1, and then it's like,
Ma'am,
yeah,
ma'am, can you scroll up to the previous slide?
yeah, this one.
Ma'am, here, yeah, here. Ma'am, if we do the dot product with 100 with that grad f, that means alpha plus beta, comma 2 beta plus gamma, comma 2 gamma,
Mhm.
and take its norm and equate it with magnitude 5, then am I right or wrong? Is this process?
Here we want the maximum value. So then if we take this, wait, the dot product of what and what?
Actually, ma'am, here we need to find the directional derivative parallel to x-axis. That means 100.
Hmm.
So if we do the dot product with 100 and that grad of f 111,
Hmm.
those two vector, then if we take the norm of that vector and equate it with 5,
Mm-hmm.
is this correct or wrong, ma'am?
Mm, so the gradient is, when you take the dot part, what is going to happen is it's going to become like it won't stay a vector. It's just going to be a real number value only, because 100 into whatever here. So basically, these two terms are going to get multiplied by zero, and then we're just left
Mhm.
with one times alpha plus beta. So that is going to be a constant. It's not going to stay a vector. So then we can't take the norm of a constant, right? It's just a constant. So that is an issue there.
Okay.
Yeah. So what you like, the norm, the dot product thing comes in when the function isn't changing at all. So this whole thing is going to be equal to zero. So that is why, because the function isn't changing, this whole thing has to be equal to zero. Then we just want a u such that the u dot product with this gradient has to be zero. That is it. So
Okay.
if you
Okay.
want like When we take the dot product and all that, that is for like the actual value of the function.
Hmm. Hmm.
Yeah.
Okay, ma'am.
Yeah. So let's just see, like, yeah. So all of this, like, some theory and all that, you use it to get to the tangent line. This is from the lecture. I just took it from Solve with Us. So I just directly want, it's going, like, we're going to put this PDF. It's there. So let's just directly go to the problem. Okay. So here we have a function f of xy is equal to x square plus y square, and which of the following is the tangent at the point 1 2 in the direction 1 1. Okay, so here let's see the tangent part only. Okay, so as like from this particular problem, what we have here, these are parametric equations, because we have, like, in terms of t, basically they've given like these functions of x, y, and z, and the parameter is t. So these are parametric functions, okay? And so when we have parametric functions, the equation of the tangent line, okay, so that has this form. So xi of t, that is equal to, so this is the point. So the first coordinate of the point is going to come for the x part, plus then t times whatever unit vector you have. So we'll just apply this here. So once you do it, it's going to become clear. Okay. So here we have x square plus y square. Okay, we want the tangent at the point 1 2 in the direction of 1 1. So because it's in the direction of 1 1, that means we, because as per this, we need a unit vector just from the parametric equation form. So in the direction of unit vector only, then we can use this form. So let's calculate, let's make this a unit vector. So what is the unit vector here? 1 second, I'll just zoom up. Okay, yeah, yeah. So U is basically what they've given, like, say this is V, then. This is V. Okay, in the direction of. So U is the unit vector. That means this is going to be V by norm of V. So here that is equal to, what is this equal to here? We have 1 1 as it is. What is the norm of 1 1?
Root 2.
Yeah. So square root of 1 square plus 1 square, just root 2. Okay, that is what we have. 1 second. Okay, so this is just the unit vector. Okay, so we have this. So from this we can write it in like the form u1 and then u2, so that we can like take out each coordinate, because in parametric equations you have like for x, y, and z and all that. So we can rewrite this. U is equal to 1 by root 2, 1 by root 2. Okay, so I just took this vector, I wrote it in full vector form. So this is basically u1, u2. Okay, so this is the direction in which we want the tangent. Okay, and we want it at the point 1 2. Okay, so we'll just evaluate the function at 1 2, but not the function though. They've said we have to evaluate the gradient. Okay, so what this particular thing here, I'll just zoom in again. Okay, so here this notation means that it's the gradient or the directional derivative at this point. So what we'll do first is, for this given f, we'll find the directional derivative or just the gradient vector. Okay, let's just do that. So for this given f, So what is going to be this vector for this function? F of xi is equal to x square plus y square. Anyone? What is the gradient vector?
Ma'am, gradient into vector, unit vector.
No, no, just the gradient vector of a function. Okay, we just went through this.
Partial derivative with x and y.
Yeah, so the first element is just the partial derivative of the function with respect to x. So here, what is the partial derivative of this with respect to x?
2x.
Exactly. So the first element is just 2x.
And 2y.
Yeah. Okay, so that is it. Now in this, we'll put in the given point. So the given point is 1, 2, right? Here we have 1, 2. So we just put 1 and 2.
Ma'am, can you just say how did we find u is equal to v by norm v?
So they've given us, they want it in the direction of this v. This is v, right? So u is the unit vector in the same direction. So we just take that vector divided by its norm.
Yes, ma'am.
So gradient of f at the given point 1, 2. So here we just put in 1, 2 in place of x and y. So what do we have? That is equal to what? We're taking x is equal to 1, y is equal to putting it in this. So what do we get? 2 times 1,
2
right?
comma 4.
Exactly. That's it. That's all we have to do. And now we just match it to the given parametric equation form. Okay. So here,
Ma'am, can you enlarge a bit, ma'am? I cannot, no, cannot see properly.
yeah. Okay. So here we want to match it to the form. So first, as per the given parametric equations, okay, so this first ai is just like the first coordinate of the point given. So here we are evaluating at the point 1, 2. So here it's going to be x plus x is equal to 1 plus something. Okay, and the next part t of ui. Okay, so that is going to be t times whatever you have. So we found out that u1 is basically 1 by root 2. So also the point, I'll write that also. I'll just write everything in one place. Okay. So point, this is 1, 2. Okay. So this is A, A1, this is A2. This is here, this is U1, this is U2. So we have to like write it out in terms of the coordinates. So the first parametric equation, x, this is in terms of t. They didn't write t here, but that has to be there, okay? So that is equal to, the form is a1 plus t times u1 times t. T is like some random parameter. So in our case, we have a1 is equal to 1 plus u1 is 1 by root 2. So t into 1 by root 2 is just t by root 2. That is the first parametric equation. So we can see here that the first option only matches it, but let's just calculate the rest also. Okay.
How did we do A1 plus U1T? Like if
That is the parametric equation form. Okay, so it's discussed in lectures. This is like a specific kind of equation, and when you like write out, you have like uh, parametric equations. You have as many as you have variables. Okay, so here we have x and y, so we'll have those, and we also have another z, like a parametric equation with respect to z, and z is basically the value of the function. And the form is that for each parametric equation, ai is like the coordinate, like ith coordinate of the point that you've been given. So you are finding out the functions, like the equation of the tangent line of the function at some point, right? So the point is a tilde. So ai is the ith coordinate of that point, and then you are adding to that t. T is just this parameter from the parametric function. So that t is going to stay there, and then ui. So because it's in the direction of this unit vector, ui is the ith coordinate point of this of, of this unit vector that you find the direction in terms of. So here we found out that they gave it to us that we wanted it in the direction of this 1 1. So first we got the unit vector in that same direction. So we divided, so this is how we did it. We divided by the norm of that vector. Okay, so this is a unit vector. So the first coordinate is u1, the second coordinate is u2. Now the point they've given is 1, 2. So the first coordinate is a1, the second coordinate is a2. So if you have like, this is in xy. So if you have more elements, then like you would have a3 if this was like xyz, etc. So parametric equations generally you will have for xyz only. This is always the same form. So it's discussed in the lectures, but this I took from the solve with us question like activity thing. So go through this if you want to like get familiar with the form. So that is like always there. Sorry. Yeah. So now we need it for y also because we have f of x y. Okay. So the parametric equation here, I'll just zoom out again so we can see the whole thing. Okay. This is equal to a2 plus u2t. Now, t is just some parameter, you don't have to worry about it, it's just going to be there. So here, what is going to be this parametric equation then? Like if we follow this exact form, okay, we have defined everything. So what is going to be this parametric equation? We have a2. A2 is directly coming, it's the second quadrant of the given point, right? So a2. So we have 2 plus u2, we already found it's the second coordinate of the unit vector, and so t u2. That is all there is to this. Same approach each time. And we can also get z of t. So z is the value of the function. Okay. So here, what they have done is this whole thing is equal to z. Okay, the function f of xy, that is z. So z is equal to xy plus y square. So at this point, 1, 2, okay, z, that is equal to f of x, y, that is equal to x squared plus y squared. So at this given point 1, 2, z is equal to 1 square plus 2 square, that is equal to 1 plus 4, we have 5. Okay, and then you can see this here. This is the value of the function at that point, and then you have t times the derivative at that vector times at that point. Okay, so here we need to compute basically f of u x y. So this is another way to write directional derivative. So normally we'll have d here. I'll just write d only. So we know. But in this here they've used f. Okay. Here for z of t, they've taken the value of the function at that point and then t times the directional derivative at that point. So here instead of d they've used f, but I'm using d only. It's the same thing. Okay. So this is what we're finding. Now we saw earlier the directional derivative in the direction of some unit vector is that unit vector. Okay, we take the dot product with the gradient, and we have all of these values here, right? We computed each and every one of this. So here, and also, okay, let's just write the general form out first. Okay, now so here that means that we have u we have as 1 by root 2 times 1 by root 2 comma 1 by root 2. So 1 by root 2 comma 1 by root 2, taking the dot product, and this gradient we found out 2x 2y. Okay, so we can also rewrite this as like a full equation that is equal to 1 by root 2 2x plus 1 by root 2 2y. So now if we put in the value of x and y that we have, that is the point. From the point that we've been given, we'll take x and y. So du of 1 to, that is equal to, so now we just put in the values then, 1 by root 2, 2 times 1 plus 1 by root 2, 2 times 2. Okay, we're putting in 2 for y. That is equal to, so 2 by root 2 plus 4 by root 2, that is equal to 6 by root 2. I'm not simplifying, I'm not cancelling out the root 2 from the denominator, I'm keeping it as it is. Okay, so now let's get the parametric equation for z. So z of t is equal to the value of the function f of 1 2 plus t times the directional derivative at 1 2. So that is, we found out that the value of the function is 5 plus t times 6 by root 2. So that is 5 plus 6t by root 2. And as you can see, this matches like this the option that we have. Right? So let's just go through this once. Okay, this is going to be a standard approach each time. So generally you'll have x, y. If some z is given, then based on that, like you will, like if there is an additional z variable, then you'll get the z of t like you did for x and y. But in case of like when you're asked to get the parametric equations, generally you'll just have f x and y. Okay, so this is the approach. We want the parametric equations for like the tangent at the point 1 2. So we want to evaluate at 1 2, and the direction they've given is 1. Okay, so from that, the direction we have to get the unit vector. So we normalized it or divided by its norm, and we got this unit vector. And we also had to take the gradient vector of the given function. So we found that, and we also had to evaluate it at the given point. So we did that. Then the parametric equations become the variable x that you have, the parametric equation with respect to t, that is a1 plus u1t. So a1 comes directly from the point, and then u1 comes from the first coordinate of the unit vector times t. So for x and y, it's fine. Then for the z, what is a is just the value of the function when you put in this point. So when I put in 1 2 in the original function, that is my z. Okay, that plus t times the directional derivative of the function in at 1 2. So the point is staying put. So we did that also. We found first the directional derivative of the function. Okay, that is just the dot product of the gradient times the unit vector. So you got this equation. We put in the given point. So we have this, and the general form is always some constant plus t times some constant. Okay, so here also we did that, and we got it. So this is the standard approach to get the tangent in terms of parametric equations. Is it clear? Any doubts? Okay, so we have another problem, but it's basically the same type. So I'll just show it to you. Okay, so there's this one last problem. This is exactly what we saw above, but here we have a different function. So, and this is f(x, y, z). Okay, so in this case, we get x like the parametric equation for x as we did above. Okay, we get it for y also as we did above, and we get it for z also as we did above. And u of t is like here we found out for some z, here that's u. Okay, so there's always going to be one more parametric equation than the number of variables you have. Okay, so the approach is still the same. This whole thing is being set equal to u. So u of xyz is going to be this value, and then to get,
Excuse me, ma'am. Please enlarge the view, ma'am.
yeah, sorry, yeah, sorry. Okay, so this whole thing is u. Like here we saw that this whole thing only was setting equal to z. Here similarly, because it's already xyz, we have to introduce a new variable, that is u they've taken here. Okay, so u is equal to this value. So when you put in 101 in this, that is u. So as you can see here, u is going to be just 0, like, because at this point 1 into 0 into 1, that is going to come to 0. So that's why you can see in all of these you don't have some constant plus t times something, because the first value is going to 0, right? So this problem is the same. So let's go through it though. Okay, so first we'll get u. So u is basically f of xyz at the given point. So 101, that is equal to 0. Okay, that we have. And what else do we need to find in this case? we need to find the gradient obviously. So let's get that also. So gradient of this function. So it's like a vector with three elements. So what is the first element? Let's just do that. X, Y, Z is the function. The first element has to be the partial derivative with respect to x.
Why is it?
Yeah, we have y, z, and the
Yes,
next one x, z, and then we have x, y.
why? XY.
Yeah. So now we'll directly put in this point also, get it in 1 year. So 101, that is equal to, so y z is just 0, x z is 1, and x y is again 0. Okay. So we have this. Okay. So now we also have in the direction of this 111. So we need to normalize it, right? So the direction, that's also u, but let's call it v here because they're already using u in like this parametric equation. So we'll say in the direction of v is equal to 111 divided by the norm. So what we're left with, this is the unit vector v. So 111, the norm of this is 1 square plus 1 square plus 1 square, that is equal to root 3. Right? So 1 by root 3, 1, that is just this vector, the unit vector in the direction of which we'll find this. We have everything we need now. So now we also need for this last parametric equation, we also need the directional derivative of the function in the direction of this unit vector. So here the unit vector I'm calling it v. So f or we could just directly write that this is just the gradient because we're just multiplying it out. So gradient f and we're multiplying it by v for this point 101. So that is equal to, so from v's first element we'll have 1 by root 3. Okay, and then what we have here, oh, oh, so what we're left with, because each of these elements in this is going to be, the first one is going to be 0 times 0 plus 1 by root 3 times 1. 1 second, zoom out. I'll just rewrite this here. Okay, to avoid confusion, I'm writing this as v, but to stick to r form, I'll rewrite this as u. Okay, and this is our unit vector. I'll specify that unit vector parametric equation. So now, for we need to compute to get the parametric equation for u in terms like ut. We got this, the value of the function at 101, that is just 0. So we have this, and we also need the directional derivative of the function. Okay, so that is just gradient f into the unit vector at point 101. So that is 1 by root 3. Okay, and so at 101, we already found out that the first element is going to be 0. So this is 0 plus 1 by root 3 times 1 plus 1 by root 3 times 0. Okay, I just did it all out for clarity, but we can see that this is equal to just 1 by root 3. So we can now have our equations. So for x of t, the first element is just the first coordinate point. So that is 1. That is coming from this. This is the given point. So that is 1 plus t times u1, right? U1 comes from each of these. So I'll just rewrite the unit vector properly. U is equal to 1 by root 3, comma 1 by root 3, comma 1 by root 3. So this is u1, u2, u3. And here, this is a1, a2, a3. Okay. So for x of t, we have 1, that is a1 plus t times u1. So that is just 1 by root 3. So we write t by root 3. Okay. Y of t, so we have a2 plus t by u2. So t times u2. So what is this? A2 we can see is 0 from this, right? So the first, like we don't have a constant term in the front. So the next part is just t times root 3, 1 by root 3, that is t by root 3. Then for z, the parametric equation. Now this, what is, so as per the form, this has to be a3 plus t times u3. So what is z? Parametric equation for z. Anyone?
Ma'am, please enlarge the view. Can't. Okay.
Yeah. So what is this we're waiting for? So in general, the form is always a1 plus t u1, or if you have like I random like xn variables, and then for each xi ith variable xi t, that is equal to ai. So the ith coordinate of the given point plus p ui. Okay, this is the general form. So based on this, y we can also think of as x2t, right? So based on this, we have, this is the point given to us. So we have a1, a2, a3 from there. The direction is given to us. So we got the unit vector from that. That is this. So this is u1, u2, u3. So x, the parametric equation for x, that became a1. So a1 came from just this plus t, the parameter, into u1. So I did that. For y, it's going to be a2 plus t times u2. So we did that because a2 is just 0 here, no constant term. So what is it going to be for z? Anyone? It's just a3 plus t times u3, right? So a3 is 1 plus t times u3 is just t by root 3. So we have this, and the last one that they've given us ut, that is equal to, so the first part is the value of the function u is just the value of the function at the given point. So we found this, that is coming to 0. so we won't have a constant term, plus t times the gradient of the function at the endpoints, that is 0, 1, 3. Oh, sorry. That is the dot product of the gradient times the unit vector that we have at this point. So from that we just got 1 by root 3. So for the last ut, this is the general form I'll specify that. So ut, so this is the value of the function we got as 0, so nothing. And then t times 1 by root 3, root 3. That is all there is to this. Okay. So based on this, we can see which one is the answer. No, it's not the last one. Okay. It's not. Yeah. So the first one has to be the answer because yeah, it just matches. Okay. So as you saw here in the previous example and the one that we saw just now, the process is exactly the same. Okay. It's just that the number of uh, variables, based on that you have plus one. No, like if the number of variables is 3, then you'll have 4 parametric equations to find. And for the last one, you'll take, like instead of like a, we generally take which is the ith coordinate of the given point. For the last particular parametric function, that is going to become the value of the function at the given point. And then instead of taking the unit vector, you will take the gradient times the unit vector. Okay. So this is all we had for today. Any doubts here? There's going to be another session, week 10. So we'll do tangent planes, hyperplanes, and critical points in that. So today's function was mainly about um, gradient, directional derivatives, and parametric equations. Okay, is everyone clear? Like no doubt
Yes,
what
ma'am.
we saw, right? All right. So I'll stop the recording for today.